Welcome to this video on Faraday's law. Here we're putting a finishing touch onto all the videos of magnetism that we've done up to this point, well, specifically on magnetic induction, because what we're going to do now is formalize a few of the statements into one coherent statement that really encompasses it all. So let's jump right into it. So just making sure that we are developing the ideas that we've already structured, we're going to say that the magnetic flux that's symbolized with phi sub b is equal to b dot a. Now we know that what could actually happen here is that this could be an integral b dot dA, and if the area is then added together and we make it a more generic statement, if the magnetic field is changing, of course, or it's constant in this case, we could just write it as b times a. Now we can write it as b times a also if the dot product, if the angle between the area vector and the magnetic field lines is 0 or 180 degrees. Now I think that I actually forgot to say in one of the previous videos, but the unit for the magnetic flux is going to be the Weber. Sometimes people pronounce it the Weber, but it's rather the Weber. And if we had 1 Weber, we would say that's 1 WB. And that's the same thing as a Tesla meter squared, which we can see makes total sense from this. Now we know that if we took this magnet and we had this field and we had this loop of area and we changed that amount of flux, so we moved the magnet either into the field or out of the field, what would happen is we would generate an EMF in this loop. And the way that we showed it up to this point was we wrote that the EMF is equal to the change in the flux over time, or the rate of change of flux. Now this isn't incorrect, but it's just missing a little bit more information, and so we're going to add a few things to it. The first thing that we want to do is we want to be able to say that it could be instantaneous, so we could take the derivative of the flux with respect to time, and in addition to that, if we wanted to represent Lenz's law in this statement, we would need to say that the change in flux is always opposed in the loop. And so we'll put this negative sign out in the front, and the minus sign there describes Lenz's law. So just in that one letter, we could have a whole lot of information. So the change in flux, remember, is always opposed, and so we would write it in this statement. Now, realistically speaking, you very seldom will have just one loop. You're oftentimes going to have a solenoid of some kind or multiple loops of wire on top of one another. And so what we could say is the EMF generated in each loop or each turn of the wire, you could multiply that by n number of turns. So I could actually go ahead and say that the EMF is equal to the minus sign for Lenz's law times n number of turns d phi dt. So just like this. And this now is a much more useful form of Faraday's law. And what it says is that EMF is generated through an opposition to the change in flux. The rate at which that happens determines how much EMF is generated. So if we make a graph here, let's make a graph that is magnetic flux versus time. What we see is as long as there is some sort of a slope here, that this slope, or the derivative of this function, so in this case we'll just write this here as d phi dt, this is going to actually tell us the EMF, and we need to make sure we take the negative derivative of that. Now if this graph flattened out like this or became constant, in this region right here, this is showing that there's no change in flux. And if there's no change in flux, then that means that there is no EMF generated. So we can look at the different rates of change. Now if the rates of change are constantly changing, or perhaps if there's some sort of curve in the change, either way, finding the derivative of this function will give me the EMF function. We just have to always remember that we're going to flip this around. Now one last thing that we're going to look at here is if we had a magnetic field that's, say, set up by this bar magnet. So let's just focus on just a portion of it down here. So I'm not going to draw the full continuous lines, but let's say I have these magnetic field lines pointing straight down. And I'm going to change this giant loop that I have here to a smaller loop and actually make it a rectangle as well. So I'm going to say I have this little rectangle and of wire, and I want to pull this left or push it to the right, and I want to let that vary the magnetic field. So pulling it to the left or to the right, would I be able to use this function in order to find that information? And the answer is yes, because it comes up in a really different perspective, even though it's coming from exactly the same law. So let's go ahead and try that out. So what I'm going to do here is I'm going to say that the EMF is equal to, and I'm going to expand this. I'm going to say that the magnetic field is constant, but the amount of area that is experiencing the magnetic field is varying. So in the way, I'm going to write it as B dA dt in this form. Okay, now I wrote dA because I know that that is changing slightly as I pull one way or the other. Now I know that what's happening here, let's draw this from a different perspective. So I'm going to make the magnetic field be pointing into the plane of the screen here, and I'm going to draw the square that I have, that rectangle of wire, like this. Okay, so we're looking at it from a different perspective, and now I'm going to be, let's say I'm pulling this out of the field this way. So I can see that the amount of magnetic flux is changing. And what I'm going to do here is say that this length of wire is outside of the magnetic field. These lengths of wire are changing whether they're in the magnetic field or not. And this side of the wire is in the magnetic field until it's not. And so what I'm going to say here is I'm going to call this the length, and I'll call this the width. Now I know that oftentimes you make the smaller one the width just by convention, but we'll keep it this way. And what we're going to do now is say that the area is equal to the length times the width. So what I'm going to do here is say that the magnetic field value is constant. And now dA, I'm going to change this. Now, instead of putting it as dA, I'm going to leave out the integral part for right now just to simplify the situation, and I'm going to look at just B times A. Okay, so B times A, and A is equal to length times width. Okay, and that's all over the time that is passing. So what I can see here now is that the amount of width that is in the field is varying as time varies. So essentially what I'm saying here is I'm restructuring this to be B times L, this constant length that isn't varying as time passes, times that width value over the time. Now, what I could say is that the D comes back into the fact that that is changing. Now, a lot of times what you can do is if width is making you feel a little confused, let's change it to X, because what we can then see is that dx dt is actually the velocity that it's moving out of the field with. So it's negative BL, and then this is dV, or we could just put the velocity here. So another way that we could write Faraday's law is not only in this form over here, but we could also write it in the form of negative BLV. And this works if we're pulling the magnetic field out of the field or if we're pushing it into the field. And that would depend on whether the flux is increasing or decreasing. So here, looks very different than this form, but could be shown just the same way. And in addition, we can always add an n in the front for the number of turns that are occurring. So here we have two forms of Faraday's law that can be very useful in different circumstances depending on whether we're solving for a single coil or a coil where we know the total amount of flux change over time, or here where we're looking at a coil moving out or into the field. Another time that this equation can become very useful is if you're looking at a magnetic field. I'll draw this one up here, and you have a bar. Instead of being a coil now, this is actually just a solid metal bar. And as this bar falls through the field, what we can see happen is that the electrons inside the bar, any free electrons that are free to move around, are going to be pulled in a direction. In this case, they're going to be kind of accumulated over here on the left, making this side of the bar negative and this side by default more positive. So we're generating a little current in here, or an EMF in here, as this bar falls with X amount of velocity through the field. And we could graph the amount of EMF that's generated across the bar by how fast it's falling. And you can see that the faster it moves, the more EMF is generated. So I hope that helps summarize things into a usable form, and we'll take a look at inductor circuits next and how we can put some of these things to work.